Hey everyone, Bionic here, and welcome back to another math project. I'm just finishing up my semester right now, and I want to do another one of these so that I can go over and teach some more about mathematics to y'all. So if you're interested, feel free to like this video, and of course, subscribe. Anyways, to get started with this, I've split up the unit that I'm gonna be working on into 5 parts, kind of somewhat related to what my teacher went over in our math class. So first is part one. Now for part one, one of the first things that we are asked to do is actually to plot our equation. Now for those of you who don't know, x squared plus y squared is the same thing as r squared, and r is representative of radius. So another important thing actually to recognize here before I go on is that um, as we switch over to my screen, we can do this plot on both of our paper and on Mathematica, which is a process we'll be using today. But I'll mostly be switching between these two things. So the other thing I wanted to share real quick was that r is actually equal to z. And this becomes very important when we get, for that first part, part A, that z is equal to 1, 4, and 9. So, really what this is that z squared equals to r. So what we do with this is, since these are all this, you would go and say radius is actually equal to 1, 2, and 3. And then with our plot over here, say we just draw something like this, go out 1, 2, 3. As you can see there, we would draw one circle and then a second and then a third right here. Mind you, my circles won't be exactly perfect, but this is really what we just need to get through for this. Secondly, we need to go and pick a few points to plug into this right here. This is basically the derivative of each part of this function right here. So basically what you go and do is let's label this as A. We take this right here and take the derivative according to x, so dx and dy, and the derivative according to x is equal to 2x, and the derivative according to y is 2y. Now, if you haven't gone over derivatives before, I would highly recommend, with getting a foot into it, to look at more calculus videos from previous to multivariable calculus, such as videos from Calculus 1 or Calculus 2, as these will help you to understand why we're able to do this process right here. But next, what we'll do is we will label this as this kind of upside down triangle, or delta, of f equal to 2x and 2y. Next, what we will go and do is we're going to take a group of values. Let's just say 1, 0, and 0, 1, 2, 0, and 0, -2, then maybe -3, 0, and 0, 3, just so we get marks on our circle, and plug them into this right here. So for example, for this first one, we would get 2, 0, and 0, 2. Then we would get 4 comma 0 and 0 comma -4. And then lastly, we would get -6 comma 0 and then 0 comma 6. So then we would go and we would take these points and I actually put a few more of them into like my Mathematica so we could actually see a visual of it. And you would put it into something that looked a little bit like this. So from what we can see here, all of the points that we've put in have this sort of gradient is what it's called, but it's an arrow map that shows us that all of our functions, or rather all of the circles, are pointing in the outward direction. I won't go, again, I won't go into details with this because I'm trying to make a shorter video just to explain these math problems, but the importance of this is later on, this will help you in order to kind of distinguish specific equations once you get further into integrals, which is basically like an antiderivative, as well as into like multivariable integrals. But the last thing that we would do is actually part C, which wants us to go and take our original function and actually plot it into Mathematica. All right, as we scroll down here, we can actually see what it would be like to produce this sort of graph in here. So from our original worksheet, we had z is equal to 1, 1, 4, and 9 right here. And those actually become these planes we can see. So, for example, 9 is this red plane, 4 is this green plane, and 1 is this blue plane. And those show us kind of the different, hold on, let me move that, the different layers of circles. But when z is equal to an x squared plus y squared, what actually ends up happening is, and it's not very clear to see here, but if we look down on this plane, this flat plane, is the x and y plane. And the cone actually that's formed by this is going down or down if you're getting smaller or up if you're getting bigger along the z-axis. And this just kind of allows us to see that there are multiple different layers. And if I were to change these different coordinates up here, then we would probably see this cone expand further up. But for now, this is kind of what we have here. All right. The next thing that we have is part 2, which has us focusing on those partial derivatives, basically what we were talking about with our last problem. So what we're going to do is we're going to take this equation right here, the x squared y cubed plus 2xy, and take the dx and dy, which for this would be a 2xy to the third plus 2y. And for this down here, this would be 3x squared y squared plus 2x. And those would be our dx and dy. But for the second part that we have right here, these ones, this is kind of easier to see in a matrix. Now, for those of you who might not have taken linear algebra but are familiar with the concept, a matrix is kind of like a way to show a set of numbers in order to solve different formulas without having the complexity of writing something out over a long span. It'll make a bit more sense later on, but for example, This is the x column and this is the y column, x and y. So this x and this y are representative of the dx and dy. And so we take the x derivative of the dx and then the x derivative of the dy. So you label these real quick. And then we do that same thing taking the y derivative of the dx and the y derivative of the dy. So for example, we would get because we got this here, we would get just a 2y to the third because there's no x in this second part. For our y's, we would end up getting a 6x squared y, and then no 2x because once again that is this part doesn't have a y in it. And then what's actually interesting is our xy and our yx actually end up being the same thing. They end up being this 6xy squared plus 2. 6xy squared plus 2. And just to kind of show you why that is, with this one we can see right here, this would be a 6xy squared because this 3 would come down with 2. And because this is a y, we'd be taking that out of there, and this would just be a 2. And that same sort of thing here with the x, taking that out, that would be once again a 6. That would be a y squared, that would be an x, and that would be a plus 2 once again. But next, what we do is we are now given a directional derivative. Basically, this just points us to where our equation is going. So what you want to do for something like this is you go in and you take your original f of x and f of y, or rather d of x and dy, and you go ahead and put in our p values right here, the 1 and the 2. So we take those values and we go and say, okay, since our dp, excuse me, that is in the middle of the page. I'll write over here. Our p is equal to a 1, 2. This is x are x and this x is our y. Then we can go back into our original equation and go 2 times 1 times 2 to the third plus 2 times 2, which ends up equaling to 20, and this other one of dy would be 3 times 1 squared times 2 squared plus a 2 times 1, which ends up with 14. So now that we have these two numbers, we actually write them off to the side like this, 20 and 14. And then what we do with those numbers is we actually multiply them by these u values, the 3 and the negative 4. And we dot them specifically. So I'll write that out as 3, negative 4. So what we do with that is we go 20 times 3 plus, that's the important part with dotting, 14 times a negative 4. But more specifically, we do that over the 3 squared plus a negative 4 squared square rooted. Now this is actually really nice because it gives us nice even numbers because this is 60, subtracting, I think it's a 56 all over 5 because these end up equaling to 25, and the square root of 25 is of course 5. and then we end up getting 4/5. And then, finally, for our last equation, now we actually get to problem number 3. And this is actually kind of an interesting one because we're seeing these new um, symbols right here. I'll actually draw them a little bit bigger, but we have this weird kind of D thing and then an F over the weird D thing, kind of like a backwards 6 and a U. And then we also have that same sort of thing on top with the D and the V. But basically what this is we're trying to get the derivative of our our f over u and our f over v. Now this will make sense a little bit later, but for now what we're going to do is, since we have all of these formulas, we are actually going to write something out. So first we'll write out dx and dy, and then we'll write out du and dv. And specifically du of x and dv of y. So first off, we have the dx, which is equal to 2xy to the third, and of course the dy, which is equal to a 3x squared y squared. And then we transition over to here. So this du of x is representative of this because it is that x equation. And what we basically go and do is, since we're looking for u in particular, we actually don't take this v into account. I should have circled it though. But we write that is 2u, and then we do that same thing for the y, just accounting for the v, and go 2uv. All right. For future reference, I will actually turn you over to my Mathematica right now because that will allow us to kind of see those parts a little bit better. But actually, before I do that, let me actually set up the equation real quick so that y'all can see it. What we then do is something like this. Dx times dux plus a dy times a dvy. And this actually looks really kind of simple. We just go ahead and write that as a 2xy cubed times a 2u plus a 3x squared y squared times a 2uv. And then after that, what you do is you actually take these values, these ones back up here, the x and the y values, and you actually plug them in here. So I'm just going to do it with this first part and go 2 times a u squared plus v times a uv squared. I think that was cubed times 2u. And then you would continue to do practice with this v right here. But now we're going to turn our attention over to the Mathematica, where I have plugged everything into notation. So as we can see here on the Mathematica, I've typed in kind of an interesting way of looking at stuff. You need to actually do the underscores next to everything, just because of the formatting of Mathematica. But basically what this does is I've plugged in our f of xy right here, and then I've plugged in our x of uv and our y of uv. And those are the same thing as the x equals 2x squared plus v, or not x squared, u squared plus v, and y equals 2ruv squared, as you can see up here. Then we do a function where we use the capital D to get these values completely computed. And this actually makes Mathematica really nice to use because you can take a lot of the complex work that you would do with a problem like this and just plug it in and get the answers usually more correct than how you would get them yourself. But our end result actually ended up being for our df over du is equal to a 4u to the fourth v to the sixth times u squared plus v plus a 3u squared v to the sixth times u squared plus v squared plus v parentheses squared. And then our second part ended up being a 2u to the third v to the sixth times u squared plus v plus a 6u cubed v uh, to the fifth times a u squared plus v that's been squared. And that ends our third part of this segment. Now, as we move on, we're moving on to our fourth part. So, our fourth part, I decided to do mostly in Mathematica. And that's just because it's a little bit easier to explain, but there's something that I wanted to show you that's really nice for remembering things later on. Something important to remember is sometimes when you're graphing, you might come across kind of an interesting set of values. I'm just going to put up coordinates to represent this, but you might come across something like this. Let's just go 0, -1, -1, 0, a1, 0, or a0, 1. So in a lot of situations, we'll represent 0 as a positive value, and we'll represent any negative values as just being negative. So I'm actually going to change these both to negative values just to make this example a little bit easier to see. So negative, negative, positive. Now you see these signs the way that they match up. These actually help us to see what type of mins and maxes we might have in an equation. Now, if any of you remember, mins and maxes are points reached on a slope where we see the most kind of growth in a chart. And something specific that's kind of nice about remembering these is there are actually some faces that are kind of used, at least the way my teacher taught it, that are easy to remember. So we have this, and we have this. And these two faces are represented by positive, negative, or negative, positive. They kind of have the same shape, and the shape is described as a saddle. They're kind of the confused faces. We have this face that's positive, that actually shows us the min. And then we have this face that's negative, and this shows us the max. And so by these kind of simple tricks we see here, we can tell if there's local mins and local maxes, which is another calculus subject, as well as seeing saddles, which is where we see a change in both. But for now, let's go ahead and switch back over to Mathematica. In our Mathematica, as you can see, I actually typed up both of our equations that we see on that problem. And I attached our secondary equation, our x squared plus y squared equals 1 to a g of x. But something important is that we take out the equals to 1 part of the x squared plus y squared, because that actually becomes our c. Now we take the gradient. That was the word I was forgetting on problem 1 and 2. It was that delta of f. We take our gradient of f and our gradient of g, and then we use this kind of funny looking symbol right here. This funny looking symbol, I don't remember exactly what it's called, but this actually helps us to find different equations and be able to graph things. And so what we basically do is we go and we find the gradients as we see down here. So for example, we have 2x because this was an x squared, and we have a 4y because this is 2, and then this 2 right here moves over to here. And then you see that same sort of thing happen again. And then what you would do is you'd put these in a matrix, just like we saw before. So we'd have something like 2x over 2x and 4y over 2y. And then what you actually do in here to get numbers like this is you would plug in a minus one of these to our A and to our D parts. Think about it kind of like when you're calculating in matrices for the I forget what it's called. It's like there's an end result where you do AD minus BC. But you do the same sort of thing with this symbol right here by adding it in, and so you can get specific values for that. Now, I just went down here and I actually showed you what this sort of plane would look like. So for example, this one right in the middle that has radius 1 is actually this g of x, and then all the ones we see surrounding it are actually this, with, of course, our added contours and everything like that. But with this, for example, we would take our inner circle and we would actually mark the points that we would say are mins or maxes. We don't really mark things that are saddles, but for example, we might mark here on this side over by the 1. We basically just mark all around that radius because we see many different of the mins all around and maxes all around. Now we come to the last part of our derivative assignment. We are going to be working on kind of our most complicated thing so far. Something I always like to do that I haven't done with a few of these, but I think are important is rewriting this f of xy. Any functions that you do get, it's important to go and write them down because oftentimes if you don't write them down, at least for me, I feel like I forget them. So, what we want to do here is we want to go and get, once again, our uh, d of x and our d of y from this. So we would do a 3x squared minus 3y, and then we would do a negative 3x plus a 3y squared, and those would be both calculated there. Then what we want to do is we want to, I believe, set these both kind of equal to each other. So we would go and say, maybe we take this one right here and we say our negative 3x is equal to 3y squared, except for this would be negative because it switches sides. We divide them both by negative 3, and x equals to y squared. And then we would just go and put that into perhaps an equation we already have. Now this becomes a little difficult because of what we have here, but something that makes this a little easier later on is as we plug everything into each other, like this y squared into our x squared, this becomes a 3y squared squared minus 3y. And then what we can do is take out our 3 and then a y to get y cubed plus y cubed minus 1. Now because we get this y cubed minus 1, we then know that our y is equal to a 1. And since our y is equal to a 1, and our x is equal to the same thing as our y, so we go back in, we need to take these two values and plug them into our equation like this once again. So we would go a 3x is equal to, and this is in order to get our x values, a negative 3 times 1 squared, and a 3x equal to negative 3, not negative 3, excuse me. Our 3 is x is equal to 3 times 1 squared and a 3 times 0 squared, so x equals to 0 and x equals to 1. So we can kind of see that those are the same. So now we have both of our x and our y values. So both our x and our y is equal to 1 and 0. So we would probably have those points be 0, 0, and 1, 1 as our critical points. And then lastly, we have our b. So our b is really nice because we're actually just taking the secondary derivative of basically what we've been practicing thus far. And we'll actually be able to see an example of what I was talking about before. So our dx at x is equal to 6x is equal to negative 3, and this is equal to a 6y. Now what we then go ahead and do is we plug in that symbol that I was showing y'all. It's this kind of upside down Y shape in here. 3 and then another 6 for x and y minus that. That would not be good for me to forget those. But what we basically do with those is now we plug in our coordinates up here into this, and so we get a 6 minus that upside down y, negative 3, and then the 6 minus the upside down y again for our 1, 1, and then for our 0, 0, we get just negative this, negative 3, and then the negative upside down y one last time. So from there, we actually add everything together. And because these are the same in everything, we can say that these are possible. So what we would do is we would take the value of this and square it, and the value of this and square it, as well as we would, I believe, take these negative 3's as well and add them to this, so plus 9 and plus 9. And then for our first one, we would get this y squared minus 12 upside down y plus 36 plus 9. And then for the second one, we would just get this upside down y squared plus 9. And then we would calculate for this in both equations. So for example, with this, I actually calculated both of these out in Mathematica since I'm kind of running out of room. And then finally, moving over to our Mathematica, I decided I would plug everything in because rationalizing the original formula, everything like that turned out to look a little crazy. So I'm actually going to take this out so that it's easier to see everything that happened. So let me rerun this one. Actually, let me just take out this real quick. So if we run both of these, we're actually trying to find if they are saddles or not. So we found this one on our page before, and then we found this one just by running it through. Because as it turns out, it wasn't exactly a perfect equation. That's why we have the imaginary numbers in there. And most of the time, you won't come across problems that are like this. I was just trying to make some homemade problems, so we ended up with that I value. But once again, we can see from this that this is actually another saddle. So now we can correctly identify that there are two saddle points with our equation. Awesome. Well, thank y'all so much for joining me on this mathematical adventure. I hope that you did enjoy. I know that this is probably last minute and I probably have butchered a lot of footage, but this is also my first time recording with two cameras at once and stitching this all together. So if you did enjoy, feel free to hit that like button and, of course, subscribe. That way you can catch up on my future uploads that I promise will not be math related. At least multivariable calculus related, anyways. But once again, I thank you so much. I hope you did enjoy, and I will see y'all on the next Genshin Impact episode. Take care and goodbye.